Hello, everyone. This is going to be our day 3 notes. This is going to cover units 1.5 and 1.6. And the big idea today is transformations and graphing. We saw a little bit of graphs on our last bit of notes, right? We were thinking about functions and the rate of change. And what we're going to do here is talk a little bit more generally about how common moves will affect different functions in the same way. So you can see here in our notes, transformations will change the specific points on a graph, but will keep the general shape largely intact. The way we're going to, when an equation indicates multiple transformations, we always want to follow order of operations. This is one of those nice setups here where we've spent a lot of time with order of operations, evaluating and understanding, and here we can use that work to help simplify something that can be more complicated. So following those order of operations, we start by what's inside the parentheses. You can see here the input has been affected, right? The input has been affected. When we add to the input, it moves our graph to the left, and when we subtract from the input, it moves our graph to the right. Understand that when we look at a graph, what we're really looking at is the output of the graph. So the fact that the graph shifts right or left isn't directly, it's actually kind of backwardsly related to the input. As we make that input larger, what used to happen when the input was smaller has effectively taken over, right? By adding to the input, our graph moves left. By subtracting to the input, our graph moves right. Those points, if our graph moves left, we are going to subtract C. And if we move right, we're going to add that C value. You can see that what we do inside the parentheses ends up being the opposite of what happens to the point itself. Moving on, we can deal with horizontal stretches and shrinks. This, again, is going to occur inside the parentheses. You can see in the example that multiplier, C, is inside the parentheses. And inside the parentheses, everything is messy. So what ends up happening is we take the x value and we multiply it by the reciprocal of C. Just like when we were moving right and left, we can't really trust our intuition. We have to take the reciprocal of that multiplier when we're inside the parentheses. Everything's backwards and complicated inside. So what we can see here is if that C value is greater than 1, taking the reciprocal of a number greater than 1 results in a stretch factor less than 1. That would be a shrink. If C is between 0 and 1, we're dividing by a number that's less than 1, making the values larger, and this will cause our graph to stretch. These are, I would say, the two most complicated moves. When we're dealing horizontally, we have to fight our intuition. If I am adding, it feels like we should move right, but we really move left. If I'm subtracting, it feels like we want to go left, but we move right. When I'm multiplying by 2x, it's really going to shrink horizontally by a factor of 1/2. If I'm multiplying by 1/3 x inside my parentheses, it's really going to stretch by a factor of 3. Reflections, I find them to be a little bit easier, right? The input becomes negative, so our points, our x values, flip signs. Now that we're on to step 5 here, everything is occurring outside of the parentheses, right? When we deal with order of operations, inside matters first, and then we work our way out. So our rules 5 and 6, 5 is all about the vertical stretch and shrink, right? If that C value is a stretch factor, those points become x, C, y. No need to deal with reciprocals or anything like that. If C is greater than 1, we cause a stretch. because we're multiplying our y values by a number greater than 1. If c is between 0 and 1, we get a shrink. Why is that? Well, we multiply a number by less than 1, it gets smaller. Finally, a reflection across the y-axis. If I used to have the points x and y, I now have the points x and negative y. Like I said, these kind of move from challenging to easy, right? As we go through these transformations, things get a little bit easier, right? We can trust our instincts a little bit more. So let's see what that all means. So here, I have a graph, and it's not a normal function, right? I can see that it is, kind of parabolic for part, and then maybe an absolute value for another. This may be described as a piecewise function. They want us to take this graph and transform it, right? And the way we're going to transform it is as we see here. I think one way to do this is to transform points, okay? So I'm going to start with my first graph here. I have -4, 0. I have -2, 4, 0.00, and, to -2, and 4, 0. So I have 5 points here. This is just simply x and y. So let's look at the function. What's going to happen when I transform these points? Well, I want to work inside out and figure out what happens to our x values. So the first thing I want to look at is that's not what I wanted. Let's grab a highlighter. Let's change colors. I'm really curious about here. This is all the ways in which our x values have been affected. That x minus 1 moves our whole graph right 1. And our x values are going to be what they previously were, plus 1, right? So -4 becomes -3. -2 becomes -1. 0 becomes 1. 2 becomes 3. And 4 becomes 5. Now our y values, there's a few things happening. We take our y value. We are going to multiply it by -1/2. We have a vertical reflection. We have a vertical compression by 1/2. And then we also add 3 to move the whole graph up. Again, we want to follow our order of operations. So I'm going to take my previous point, right? This is 0. I'm going to multiply that times -1/2. I still get 0. And then add 3 to it. I found the y coordinate for that first point, -3, +3. So let's go ahead and plot that point. 1, 2, 3, 1, 2, 3. We're going to go through this and calculate our other values. So when I plug in 4 for y, I'm going to multiply it by -1/2 and get -2, plus 3 is 1. I'm going to plug in 0. I multiply that by -1/2, and again, I get nothing. Plus 3 is 3. Let's see. I plug in -2, multiply that by -1/2, and get +1. +1 plus 3 is 4. And finally, I plug in 0 for a third time, and I know that the result there is going to be 3. So now I have 5 points. I'm going to go ahead and plot those on this second graph, and we will have our transformed function. So -1, +1 is there. 1, +3 is there. 3, +4 is there. Oh, sorry, I didn't count my values. 3, +4 would be there. And 5, +3 is there. So all I've done is transform the points, and now I'm going to zoom in to try to make this more appropriately shaped. So let's make this one nice and round, and then these ones are nice and straight. So we've transformed our function, right? Our graph has been vertically compressed, vertically reflected, shifted right 1 and up 3. We can do that with these points. let's move on to the back. We are going to walk through just the top of this, this idea of parent functions. We'll define our even and odd functions, and then you guys are going to do some graphing to transform some parent functions. So parent functions are, the most boring form of a function in a particular family. These five in front of you are going to be coming back over and over again. Y equals x squared. My expectation with these 5 graphs is these are stuck in your head. You know these are memorized because this is a starting point that we'll build off of. So what does a graph y equals x squared look like? It is a parabolic function with its vertex at the origin. It has that U shape that looks something like that. What does the square root function look like? Well, it's undefined. On the left-hand side of our graph, the point 1, 1 and the point 2, 4 would be on it, and it would really look like a half parabola opening sideways. The absolute value function, well, it's going to look like y equals x on the left-hand side of our graph and y equals negative x on the right, giving it that, oh, that's not very straight line. Let's undo, and let's try that again. All right, so the left-hand side of our graph will look like a linear function with a negative slope. The cubed function, this is going to be an elongated, almost S-looking graph. It is still known as a cubic parabola. It has a different shape than a quadratic parabola, and it's pretty tall and skinny. Right, cubing a number, multiplying it times itself 3 times, makes those numbers get pretty large pretty quick. Similarly, the cubed root function will behave similarly, but it'll be elongated right and left instead of up and down, as we saw with the cubed root function. So like I said, these are our 5 parent functions that you need to know, right? These are ones that we need to know as a starting point, and then we can transform these particular graphs. One thing that I find useful for each of these is like, which 5 points do we always know? For x squared, those are the 5 x's that I care about, and then these are the 5 y values we care about. Why are we using those? Well, it's the middle of our graph. They include the vertex, the most important point, and we go on from there. We can use the same 5 points for an absolute value function, right? -2 to +2. We can use those same points for a cubed function. We can use those same points for a cubed root function, right? So if I know the x values, we can choose the simplest ones, -2 to +2, and work from there. That won't quite work for a square root function, so just, a little tip here. I like to use 0, 1, 4, and 9 as my inputs that I will transform. Why? Those are integer square roots. Integers easier to work with than non-integers. All right, so let's talk about a new definition here, just to clear up some space. Even and odd functions. So visually, even functions are reflected over the vertical line, the y-axis. Sorry, let me replace that. Rather than being reflected, I really want to say that they are symmetrical over the y-axis. Symmetric over the y-axis. Mathematically, the way we would test evenness, we ask, does f of x, does it equal f of negative x. If I change the sign of the input, does the output get me the same thing? Do I get the same output when I plug in 1 and negative 1? Do I get the same output when I plug in 10 and negative 10? Do I get the same output when I plug in 100 and negative 100? If I do, then those points are mirror images over the y-axis, and we have an even function. Odd functions are symmetric over, that's OX, over the origin. Basically, they're reflected both over the x and y axis. And to test, we ask, does f of negative x, does it equal negative f of x? If I change the sign of the input, does it also change the sign of the output? That is our odd tests. And we actually do that algebraically. We'll get into that a little bit more later in Unit 1. But those are our two tests on even and oddness that we really want to be comfortable with. As we've been doing, I'd like you guys to go ahead and try to graph these transformations on your own. I will show you my answers, but I'm really going to just focus on the most complicated one. I find that to be the square root one. I'm going to take our time walking through it. But right now, I suggest you pause, try all three, and see how you did in just a minute. All right, team, let's finish this up and see how we did. So on the first two, you can see here, I have these mapped out. So I have my parent function from above, right? My x and y values. And then I took a look and see what transformations am I dealing with, right? Parent function in both cases are circled. So what's going on to this absolute value function? Well, the x values are going to go right 3. The y values are going to have a vertical reflection, a vertical stretch, and a vertical shift. So the way I show that is by taking the values from my first table and modifying them. If I'm moving 3 units to the right, my x values are going to go up by 3. If I have a vertical stretch, reflection, and shift, I need to apply those same order of operations values to get my y values. But this new table, which you can see here in blue, creates the points for my new graph. I use the same process for example B. Again, I'm shifting right, I'm reflecting vertically, and in this case, shifting up 2. I start with my parent function. I can't tell you how much easier life is going to be is if you know reliably what a parent function looks like, what x and y values you should have, right? These absolute value and quadratics, I know we've seen them before, but you definitely want to make sure you're comfortable with those starting values. The challenge one here is example C. Why is it a challenge? Well, we have a square root, already the more complicated one. We have fractions, we have negatives, we have more than one operation inside the square root. So I find it easier to figure out what the heck's going on and then kind of work there to see how I need to augment my points. Well, looking inside that operation, inside the square root, that x plus 2 tells me I'm going to shift my function to the left, and that negative tells us that we reflect over the x-axis. So the way I'm going to show that mathematically is right here. Whatever value I have for x, I'm going to shift it right 2 units, and then I'm going to turn that value negative so that my horizontal reflection is shown in the graph. So I move 2 units to the right, and then I also multiply my y values by 3 over 2. That was my vertical stretch. So, you can see here, I take my original function. These 5 points I chose because of the function, right? This is my parent of y equals the square root of x. I transform this by moving right 1, vertical, that's a horizontal reflection. And then I also have a vertical stretch. We can do this either with our graphs or we can do it with individual points. No matter what we do, we should end up with the same graph. And we are done. Thanks everybody for your attention, and thanks for hanging in there.